Ever get stuck on a coding problem that seems impossible until you see the solution is just storing subproblems? That's the power of dynamic programming. And today, we're mastering it. In this video, we will cover Dynamic Programming Practice Questions, DSA Interview Mastery Guide. Master dynamic programming with this comprehensive guide featuring 30 high-yield practice questions. In this video, we break down 30 comprehensive practice questions covering the most critical DP patterns, from knapsack and longest common subsequence to digit DP and bit masking. Before we dive in, make sure to grab a pen and paper to trace these logic paths with me. Which two properties are essential requirements for a problem to be solved efficiently using dynamic programming? Option A, greedy choice property and optimal substructure. Option B, overlapping subproblems and optimal substructure. Option C, divide and conquer and memoization. Option D, recursive structure and large input size. The correct answer is B. Dynamic programming, DP, is applicable when a problem exhibits two main traits. 1. Overlapping subproblems. This means the recursive algorithm solves the same subproblems repeatedly rather than generating new ones. 2. Optimal substructure. This means an optimal solution to the problem can be constructed from optimal solutions of its subproblems, while greedy choice belongs to greedy algorithms. And divide and conquer often involves independent subproblems. DP specifically relies on the reuse of shared subresults. In the context of dynamic programming, what is tabulation? Bottom-up approach. Option A, a technique that uses recursion and stores results in a hash map to avoid recomputation. Option B, an approach that starts from the base cases and fills an array or table iteratively toward the solution. Option C, a method to reduce the space complexity of a recursive function to O(1). Option D, a sorting technique used to organize subproblems before solving them. The correct answer is B. Tabulation is the bottom-up approach where you solve the smallest subproblems first, base cases, and use their results to fill a table, usually an array or matrix. This continues until the target value is reached. Unlike memoization, top-down, which is recursive and might hit Stack Overflow limits for large inputs, tabulation is iterative and generally more cache-friendly, though both share the same time complexity for a given DP state transition. In a 0/1 knapsack problem with $n items and capacity $W, what is the space complexity of the standard DP approach? And can it be optimized? Option A, $O, n times W, and it cannot be optimized. Option B, $O, W, and it is achieved by using a single-dimensional array updated in reverse order. Option C, $O, n, and it is achieved by using a single-dimensional array updated in forward order. Option D, $O, n times W, and it can be optimized to $O, n, by skipping redundant items. The correct answer is B. The standard DP table for 0/1 knapsack is $O, n times W, However, since the current row $I only depends on the previous row $I minus $1, we can optimize space to $O, W, Crucially, when using a 1D array, we must iterate backwards from $W down to the item's weight. If we iterated forward, we would use the same item multiple times. solving the unbounded knapsack problem instead of 0/1. Because the updated value for a smaller weight would be used to calculate a larger weight in the same pass. Given two strings, one Singapore dollar and two Singapore dollars of lengths $M and $N. If one Singapore dollar M1 equals S2 N1 dollar, what is the recurrence relation for the LCS? Option A, $LCS M N equals LCS M1 N1 dollar. Option B, $LCS M N equals 1 plus LCS M1 N1 dollar. Option C, $LCS M N equals 1 plus max LCS M1 N LCS M N1 dollar. Option D, $LCS M N equals max LCS M1 N LCS M N1 dollar. The correct answer is B. If the last characters of both strings match, they must be part of the longest common subsequence. Therefore, the length of the LCS is $1 for the matching character, plus whatever the LCS is for the remaining parts of both strings. $M minus $1 and $N minus $1. This is the fundamental reduction step for the LCS problem. What is the primary objective of the matrix chain multiplication problem? Option A, to find the result of multiplying a sequence of matrices. Option B, to find the minimum number of scalar multiplications needed to multiply a sequence of matrices. Option C, to determine if a sequence of matrices is compatible for multiplication. Option D, to perform matrix multiplication in $O n squared $time. The correct answer is B. Matrix multiplication is associative, meaning $A B C equals A B C $. However, the number of scalar multiplications can vary drastically depending on the order. For example, multiplying $10 times $100, $100 times $5, and $5 times $50 matrices in different orders can result in 75,000 vs 7,500 operations. The DP solution finds the optimal parenthesization to minimize these operations. In the edit distance, Levenshtein distance problem, which operations are typically considered to transform one string into another? Option A, insertion, deletion, and substitution. Option B, insertion, deletion, and rotation. Option C, copy, paste, and delete. Option D, substitution, transposition, and deletion. The correct answer is A. The standard edit distance problem calculates the minimum cost to transform string A to string B. Using three operations: inserting a character, deleting a character, or substituting one character for another. Each operation usually has a cost of 1. If we include transposition, swapping adjacent characters, it becomes the Damarau-Levenshtein distance. In the minimum coins version of the coin change problem, if the target amount cannot be reached with the given denominations, what should the DP state typically return? Option A, 0. Option B, -1 or infinity. Option C, the sum of all coin values. Option D, the number of coins in the largest denomination. The correct answer is B. Since we are looking for a minimum, we initialize our DP table with a value larger than any possible answer, like infinity or dollar amount plus $1. If, after processing all coins, the value at our target index remains at that initial value, it indicates the amount is unreachable. Returning -1 is a standard way to signal no solution in coding interviews. Kadane's algorithm for the maximum subarray sum is often considered a simplified DP. What is its time complexity? Option A, $O, n log n, $. Option B, $O, n squared, $. Option C, $O, n, $. Option D, $O, $1. The correct answer is C. Kadane's algorithm iterates through the array once. At each element, it decides whether to add the current element to the existing current subarray or start a new subarray beginning at the current element. This local maximum decision at each step $I is $dp I equals max I plus dp I1 $. Because it only requires one pass and a few variables, it is $O n $time and $O $1 space. When solving the diameter of a binary tree using DP, what two values are typically tracked for each node? Option A, the node's value and its depth. Option B, the height of the node and the maximum diameter found so far in its subtrees. Option C, the number of leaf nodes and the total number of nodes. Option D, the distance to the root and the distance to the nearest leaf. The correct answer is B. To calculate the diameter, the longest path between any two nodes, you need to know the height of the left and right subtrees. To see if the longest path passes through the current node, and compare that sum against the best diameter found entirely within the left or right subtrees. This is a classic example of DP on trees where the state is passed upward. What is the time complexity of solving the longest increasing subsequence? Lie. Problem using the standard dynamic programming approach, not the binary search optimization. Option A, $O, n, $. Option B, $O, n log n, $. Option C, $O, n squared, $. Option D, $O, 2 caret n, $. The correct answer is C. The standard DP approach for Lie involves two nested loops. For each element $I, we iterate through all previous elements $J, where $J less than I, to check if $ARR, J, less than arranged by I, and update the Lie ending at $I. This result in $n plus n1 plus n2 operations, which is $O n squared, The $O n log n version involves maintaining a tail array and using binary search. When calculating the $n caret th Fibonacci number using tabulation, how can you reduce the space complexity from $O n to $O $1? Option A, by using a recursive function with memoization. Option B, by only storing the two most recent values, previous and cur, instead of the entire array. Option C, by using a matrix exponentiation method. Option D, by pre-calculating all values up to $10 caret $6. The correct answer is B. The state transition for Fibonacci is $f n equals f n1 plus f n2 $. To calculate the current value, you only need the previous two values. Therefore, instead of an entire array, you can use two variables to store $f n1 and $f n2 and update them as you iterate. This reduces the space from $o n to $o1 while keeping the time complexity $o n $. In DP for wildcard matching, where asterisk matches any sequence and matches any single character, what does the state $dp I, j, $represent? Option A. The number of characters matched so far. Option B. Whether the first $I characters of the pattern match the first $j characters of the string. Option C. The length of the longest matching subsequence. Option D. The cost of transforming the pattern into the string. The correct answer is B. Wildcard matching is a Boolean DP problem. $dp I, j, $is true if the prefix of the pattern of length $I can match the prefix of the string of length $j. If the character is asterisk, the DP checks if $dp I1 j empty match or $dp I j1 match current character and keep asterisk is true. In the optimal strategy for a game, choosing coins from ends of a row, why do we take the minimum of the next move when it is the opponent's turn? Option A. Because we want to minimize our own score. Option B. Because the opponent is also playing optimally and will leave us with the worst possible outcome. Option C. Because DP always looks for the minimum value in all transitions. Option D. Because the game ends when the score is minimized. The correct answer is B. This is a minimax style DP. On your turn, you maximize your gain. However, when it's the opponent's turn, they will choose the coin that leaves you with the lowest possible subsequent score. Thus, your recursive step for your turn must account for the fact that the opponent will leave you with the minimum of the remaining options. What is the key difference between the 0/1 knapsack and the unbounded knapsack problem? Option A. Unbounded knapsack allows fractional parts of items. Option B. Unbounded knapsack allows each item to be used multiple times. Option C. Unbounded knapsack has no limit on the total weight capacity. Option D. 0/1 knapsack is solved with greedy, while unbounded is DP. The correct answer is B. In 0/1 knapsack, you have only one of each item. You either take it or leave it. In unbounded knapsack, you have an infinite supply of each item. In the DP transition for unbounded knapsack, when you take an item, you stay on the same item index $I for the next state. Whereas in 0/1, you must move to $I minus $1 or $I plus $1. What is the time complexity of the most efficient DP solution for finding the minimum cuts needed? For palindrome partitioning of a string of length $n? Option A, $O, n, $. Option B, $O, n squared, $. Option C, $O, n cubed, $. Option D, $O, 2 caret n, $. The correct answer is B. A naive DP might take $O n cubed dollar by checking if every substring is a palindrome. However, by pre-calculating a Boolean palindrome table in $O n squared dollar, we can then solve the mincut DP in another $O n squared dollar pass dollar DP. I dollar represents the mincuts for the prefix of length $I dollar. When is bitmasking typically combined with dynamic programming? Option A. When the input size $n is very large, e.g., $n greater than 10.5. Option B. When we need to represent a subset of items or visited states where $n is small, typically $n la $20. Option C. When we are dealing with floating point precision issues. Option D. When we need to find the shortest path in a DAG. The correct answer is B. Bitmask DP is used when the state needs to track which items have been used or which nodes have been visited, like in the traveling salesperson problem. Since there are $n possible subsets, this approach is only feasible for small $n. An integer's bits are used as flags to represent the set. In the classic egg-dropping puzzle with $k eggs and $n floors, what does the state $dp I, j, represent? Option A. The maximum number of floors we can check with $I eggs and $j drops. Option B. The minimum number of drops needed to find the threshold floor with $I eggs and $j floors. Option C. The probability of an egg breaking on floor $j given $I eggs. Option D. The number of eggs remaining after $j drops from floor $I. The correct answer is B. The goal is to find the worst-case minimum number of drops. $dp I, j stores this value for $I eggs and $j floors. If an egg breaks, we have $I minus $1 eggs and $x minus $1 floors to check. If it doesn't, we have $I eggs and $jx floors remaining. We take the max of these, worst case, and then minimize that over all possible floors $x. The rod cutting problem is an application of which other classic DP problem? Option A. Longest common subsequence. Option B. Unbounded knapsack. Option C. 0/1 knapsack. Option D. Matrix chain multiplication. The correct answer is B. In rod cutting, you have a rod of length $L and you want to cut it into pieces to maximize profit. Since you can cut multiple pieces of the same length, it is exactly like the unbounded knapsack problem where the weight is the length of the piece and the capacity is the total length of the rod. Which of the following problems can be space optimized to use only $O n space instead of $O n squared dollar? Option A. Edit distance. Option B. Longest common subsequence. Option C. 0/1 knapsack. Option D. All of the above. The correct answer is D. All three problems involve a 2D DP table where the current row only depends on the previous row, or the previous few elements of the current row. By using 2 rows, or 1 row with careful updates, the space complexity can be reduced from $O n squared dollar to $O n dollar. What is digit DP typically used for? Option A. Calculating the digits of pi to high precision. Option B. Counting numbers in a range $L, R, $ that satisfy a specific property related to their digits. Option C. Sorting digits within a large number. Option D. Converting numbers between different bases efficiently. The correct answer is B. Digit DP is a technique used to solve problems like, how many numbers between $1 and $10 have the sum of their digits equal to $K? It processes the number digit by digit and uses states like index, current _ sum, is _ less, is _ started, to count valid configurations without iterating through every number. What is the time complexity of the Maneker's algorithm compared to the standard DP approach for finding the longest palindromic substring? Option A. DP is $O, n squared, $. Maneker's is $O, n squared, $. Option B. DP is $O, n squared, $. Maneker's is $O, n, $. Option C. DP is $O, n cubed, $. Maneker's is $O, n squared, $. Option D. DP is $O, n log n, $. Maneker's is $O, n, $. The correct answer is B. The standard DP for longest palindromic substring involves building an $n table to check all substrings, resulting in $O, n squared, $. Maneker's algorithm is a specialized linear time algorithm, $O, n, $, that exploits the symmetry of palindromes to avoid redundant checks. If a problem asks for the number of ways to reach a certain state, which DP operation is usually performed on the subproblems? Option A, minimum. Option B, maximum. Option C, addition. Option D, multiplication. The correct answer is C. In counting problems, e.g., number of ways to climb stairs, number of paths in a grid, the total ways to reach a state is the sum of the ways to reach all previous states that can lead to it. This follows the rule of sum in combinatorics. Which shortest path algorithm uses dynamic programming to find the shortest paths between all pairs of vertices in a weighted graph? Option A. Dijkstra's algorithm. Option B. Bellman-Ford algorithm. Option C. Floyd-Warshall algorithm. Option D. Prim's algorithm. The correct answer is C. Floyd-Warshall is a classic all-pairs shortest path DP. It uses three nested loops to iteratively improve the estimate of the shortest path between any two nodes $I$ and $J$ by considering an intermediate node $K$. The state transition is $dist I, J equals min dist I, J dist I, K plus dist K, J, $. The fractional knapsack problem is best solved using Option A. Dynamic programming. Option B. Greedy algorithm. Option C. Backtracking. Option D. Bit masking. The correct answer is B. Fractional knapsack can be solved by simply sorting items by their value to weight ratio and taking as much of the best item as possible. This local optimal choice leads to a global optimal solution. DP is required for 0/1 knapsack because the greedy choice. Highest ratio doesn't guarantee the best result when you can't take fractions. In the staircase problem, climbing $n steps by taking 1 or 2 steps. What is the state transition? Option A, $F n equals F n1 plus $1. Option B, $F n equals F n1 plus F n2. Option C, $F n equals F n1 times F n2. Option D, $F n equals max F n1 F n2. The correct answer is B. To reach step $n, you must have come from either step $n minus $1 by taking 1 step, or step $n minus $2 by taking 2 steps. Therefore, the total number of ways to reach $n is the sum of the ways to reach $n minus $1 and $n minus $2. This is identical to the Fibonacci sequence. Which of the following problems can be solved using the Catalan number sequence, $C_n$? Option A. Number of unique binary search trees with $n nodes. Option B. Number of valid parenthesis expressions with $n pairs. Option C. Number of ways to triangulate a convex polygon with $n plus $2 sides. Option D. All of the above. The correct answer is D. The Catalan numbers $1, 1, 2, 5, 14, 42, appear in many combinatorial problems. The DP recurrence $C_n plus 1 equals sum C_I times C_ni. $ is used to solve all the listed problems for BSTs. Any node $I can be the root, with $I minus $1 nodes on the left and $ni nodes on the right. What is a potential disadvantage of using memoization over tabulation? Option A. It is always slower in terms of big O complexity. Option B. It may lead to a stack overflow error for deep recursion. Option C. It uses more memory than tabulation in all cases. Option D. It cannot be used for problems with optimal substructure. The correct answer is B. Memoization relies on recursion. Every recursive call adds a frame to the call stack. If the recursion depth is too high, e.g., $10 $5 or more, it can exceed the stack size limit, causing a crash. Tabulation is iterative and uses the heap via arrays, which handles much larger input sizes. Why does the maximum product subarray problem require keeping track of both the maximum and minimum product at each step? Option A. To handle floating point numbers correctly. Option B. Because a large negative number multiplied by another negative number can become a large positive number. Option C. Because the subarray must be of even length. Option D. To ensure the result is always an integer. The correct answer is B. In the maximum product subarray problem, if the current element is negative, it could turn the smallest, most negative product found so far into a new maximum. Thus, we maintain two DP states. $max underscore so underscore far dollar and $min underscore so underscore far dollar to account for the sign flipping property of multiplication. In the House Robber 3 problem, robbing houses in a binary tree where you can't rob two directly linked houses. What does the recursive function return for each node? Option A, the maximum money if the node is robbed. Option B, the maximum money if the node is not robbed. Option C, a pair of values. Max money if robbed, max money if not robbed. Option D, the total money in the subtree. The correct answer is C. For each node, we need to make an optimal decision based on its children. If we rob the current node, we cannot rob its children. If we don't rob it, we can choose the best option. Rob or don't rob. For each child, returning both values, robbed, not robbed, allows the parent to make its decision efficiently in one pass. Dynamic programming is less about a specific formula and more about a way of thinking, breaking complexity into manageable, reusable pieces. If this deep dive helped you, hit the like button and subscribe for more DSA deep dives. For the complete set of practice questions and the full certification course, check the link in the description below.